The last chapter was on interference. This one is going to be on diffraction, related phenomena, but just a little bit different. So the equations, as a matter of fact, are going to look quite similar, but the way in which you apply them is going to be a little bit different. So keep track of that. So what we're going to do is there's actually 7 sections to this, and what we're talking about the diffraction of light around a narrow opening, how a Fresnel bright spot will appear, single slit diffraction, how you get circles on these things, and sketching the different ones and knowing how they relate the different diffraction grading patterns to give you a particular type of pattern. So first of all, we're going to talk about single slit diffraction. When a wave encounters an edge, an obstacle, or an aperture the size of which is comparable to the wavelength of the waves, those waves spread out as they travel and as a result undergo interference. Those are all the key things there. Remember, the aperture has to be about the size comparable to the wavelength of the light. This type of interference is called diffraction. Waves passing through a long, narrow slit of width A, okay, and that's going to be a key thing on this. A is going to be the width of the slit. On a viewing screen, a single slit diffraction pattern that includes a central maximum, okay, bright, and then other maximum beyond that. They are separated by minimum that are located relative to the central axis by the angle theta. And this is the key equation. A sine theta equals m lambda, for m equals 1, 2, 3, whatever the different ones are, and lambda, of course, is the wavelength. And you can see where theta is on the different ones there. The maxima are located approximately halfway between the minima. Okay, waves from the top point of the 4 zones, that's shown right here, bang, 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 okay, of width A over 1/4 over 4 undergo fully destructive interference at point P. For D, which is the distance from the slit to the screen, okay, so that is almost always much larger than this slit, contrary to how it appears right here. We can approximate rays 1, rays 2, rays 3, and 4 as being parallel at angle theta to the central axis. That's the way in which it looks right here, okay? That's for this D being much larger than this area, this distance here. So, the first checkpoint. We produce a diffraction pattern on a viewing screen by means of a long, narrow slit illuminated by blue light. You're going to have to remember the relative wavelengths for blue, red, orange, and all the different ones to make sense of some of these different things. So this is blue wavelength. Does the pattern expand away from the bright center with the maximum and minimum shift away from the center, or contract towards it as we switch to yellow light, or decrease the slit width? Okay, now in both of these cases, as you go from blue to yellow, change in wavelength like that, you are going to expand the pattern shift. And as you decrease the slit width, because of where that is in the equation, okay, that's where you also are going to expand it, okay? So the answer to both of those is to expand. First practical exercise. This is problem number 1 at the end of the chapter. And it says the distance between the first and the 5th minima of a single slit diffraction pattern is 0.35 millimeters and the screen 40 centimeters away. This is your L factor. I'm sorry, this is your big D factor here, right? From the slit, the wavelength is 550 nanometers is used. Find the slit width. This is going to be your A value, right? Calculate the angle theta for the first diffraction minimum. Now, this is the equation. A sine theta equals m over lambda, we're going from the first m1 equals 1 to the fifth one, m2 equals 5. And so what we're looking at here is the distance. The delta y is the distance on the diffraction pattern. Okay, the distance on the diffraction pattern is d delta sine theta. And so this is going to be, and this is the difference in ml over a for this particular one right here. So this is the distance away that it is, and this is this equation. And so when you work with this equation, how far they are apart on the pattern down at the distance d away is going to be given by the wavelength, the slit width, and m2 minus m1. What we're trying to solve for is a. So you rearrange this equation, and we have all the different materials that all the different variables that we need there. A is going to equal d lambda over delta y, m2 minus m1. And so this right here is 400 millimeters, right? That's what we had here. It's 40 centimeters away. That means it's 400 millimeters. Wavelength of light is 550 nanometers. And what we're doing is we're putting all of these in terms of millimeters just to facilitate the way in which we look at these different things. So this is 550 times 10 to the minus 6 millimeters. And then delta y, that is 0.35 millimeters. So solving for a, we get 2.5 millimeters. Then we go back to this initial equation up here. For m equals 1, okay, sine theta is going to equal, well, for any m, it's going to be ml over a. But if this is 1, it's just the wavelength divided by that slit to give you what that angle is. That's the sine of the angle there. And the inverse sine of that in terms of radians is exactly that same value. And so radians is what we want to use here when we do this. So the inverse tangent, the inverse sine of the sine of inverse sine of this value right here is the same as this value. Okay, so practical exercise number 2, and this is problem number 3. Here we've got a wavelength of 590 nanometers incident upon a slit. Here we're given the value of a. It's 0.40 millimeters. A thin converging lens of focal length plus 70 centimeters is placed between the slit and the viewing screen and focuses the light on the screen. Okay? So, this takes information that you have from a couple of chapters ago. So, with this lens type of information, how far is the screen from the lens? Well, the plane is incident on the lens, and it's brought to focus in there, so the distance is going to be exactly equal to this same distance right here, the focal length, isn't it? Okay. Then we have to do some calculations. What's the distance on the screen from the center of the diffraction pattern to the first minimum? Okay. So that'll be m equals to 1, right? So the distance on the screen at the center of the pattern is y equals d tangent theta, where d is the distance from the lens to the screen. So for sine theta, that would be a sine theta equals m lambda, or that sine theta is ml sine. So what we do is we first solve to get what the theta is here, right? And then we can utilize that with the d to get this y value here. And so this is going to be the wavelength, 590 times 10 to the minus 9th meters. Okay. This right here is going to be 0.4 times 10 to the minus 9th meters. Again, they are doing it in terms of meters. You could have just as easily done this in terms of millimeters or whatever, because these units are going to cancel out, right? But be that as it may, this turns out actually, this is not quite right. This one down here. This is not 0.4 times 10 to the minus 9th meters, right? They screwed up there royally. This is this right here is 0.40 millimeters, which would be 0.4 times 10 to the minus 3 meters, right? No, 10 to the minus 6, 10 to the minus 6 meters, right? This is 0.4 millimeters, be 10 to the minus 6 meters. And that's why you get this value right here, 1.47 times 10. No, that would be. That would be, if this was 10 to the minus 6 millimeters, this would be just millimeters here. So this would not be there at all. This would just be 0.4 millimeters, right? And so the value here, it is minus. This is the correct answer, but they're off by a factor of 6 here, right? This should be 10 to the minus 3 meters here. And when you divide that by this right here, you do get 10 to the minus 3. And because this is in radians, theta is in radians here, when you substitute up in here, the d is going to be 0.7 meters. Tangent of 1.475 times 10 to the minus 3rd radians gives you a value for y of 1.0 times 10 to the minus 3 meters. You can see that on the overheads if you've downloaded those. That just doesn't show on the screen that I've got here. So the answer for y is 1.0 times 10 to the minus 3 meters, and this portion right here is an error. There's a couple of them on the slides that I just that they would not let me correct. Now we're going to go on to practical exercise number 3. And this is problem number 6. Here the wavelength of light is 441 nanometers, and the screen is 2 meters away. Distance between the second diffraction minimum and the central maximum is 1.50 centimeters. Here they want you to calculate the diffraction angle theta for the second minimum and to find A, the width of the slit. So first of all, theta is just going to be the inverse sine of 0.0150, right? That's this right here, the distance between these two right here. And this right here is your d value, right? So theta is going to equal 0.430, and this is in degrees, okay? For the nth diffraction, A sine theta equals m lambda, right? We all know that equation now. Solve for the slit A. It's just m lambda over sine theta. Okay, we are the second minimum, and so that's 2. Wavelength is 441 times 10 to the minus 9th meters, and this is sine of 0.430 here to give you 1.18 times 10 to the minus 4, and this value here is in meters. They I don't know, should take a few points off for them as well, because they didn't put their units here, shouldn't we? But anyway, that's that exercise. Now, the intensity of a single slit diffraction. Here we have, and a lot of times what you're going to do is you're going to be doing the ratio of these intensities. So the intensity at any given angle divided by the intensity of the center of the pattern is sine alpha squared, well, over alpha squared, right? Sine alpha over alpha with that quantity squared. And alpha in these cases is 1/2 the angle phi, the diffraction, the phase difference. Phase difference is what phi is, right? And so that would be pi a lambda sine theta, okay? So the plot shows the relative intensity in the single slit diffraction for 3 values for the ratio of A over lambda. The wider the slit, the narrower the central diffraction pattern, okay? So here you've got a very wide slit